So let me start by saying I'm mostly going to be talking here about what George Ellis called small c cosmology. At a certain point, I'll switch over to what he called large c, and you'll see that because I call it meta-cosmology, and so we won't have to worry about capitalization of letters. I'd like to start off by apologizing to everyone. One of the main messages of my talk is that in the very early universe, including the era that's commonly called inflation, the formalism of quantum field theory is just not applicable. It's not a good approximation to the real theory of quantum gravity that's really applicable in that region. And the problem is that the formalism for the real theory of quantum gravity that I'm going to use is something that Willy Fischler and I have been developing over the past decade. It's called holographic spacetime, and very few of you, I'm sure, know anything about it, but I also don't have time to explain to you very much about it. So you're going to have to take a lot of things that I say on faith. There are mathematical models that stand behind a lot of what I'm going to tell you about, but I just don't have the time to tell you about the details of those models. So everything I'm talking about is work done with Willy Fischler, TJ Torres, my graduate student who will be looking for jobs this year, so he's very good. We've published several papers on this already. We're in the middle of working on some others. A lot of what I talk about today will have to do with that as yet unpublished work. Okay, so I'm going to start with the takeaway, what you should remember. The formalism of holographic space-time differs from quantum field theory in many different ways, but one of them is that its quantum mechanics refers to the quantum mechanics along a particular time-like trajectory in space-time, and the time parameter is supposed to be the proper time along that trajectory. And to describe all of space-time, we have to use an infinite number of different quantum systems, each of them describing space-time as it's seen from a particular trajectory. So the picture is something like the following. If I think about a given time-like trajectory through space-time, I think about a fixed interval along that trajectory, it defines a causal diamond. In quantum field theory, a causal diamond corresponds to, loosely speaking, a tensor factor in the operator algebra, a subalgebra of the operator algebra that commutes with everything, quote, that's space-like with respect to it. This will be our constructive principle for quantum gravity, or one of two constructive principles. Namely, when I think about time evolution along such a time-like trajectory, it has to be such that if I break the time interval up into pieces, then the dynamics in one segment that refers to a particular causal diamond should separate the degrees of freedom out that have to do with that diamond and act only on those, plus have another piece that acts on everything else in the Hilbert space. So while the Hilbert space itself has some fixed size, the time evolution over a fixed finite time only involves a subset of the degrees of freedom corresponding to a tensor factor in the Hilbert space. The second principle is that when I have two different time-like trajectories at any time, if I look at the two causal diamonds along those trajectories, they may or may not have an intersection. That intersection region, despite what this two-dimensional picture looks like, is not itself generally a causal diamond, but there is, in a certain sense, a maximal causal diamond embedded in it. And our claim will be that that causal diamond, the avatar, if you will, of that causal diamond in the quantum theory, is a common tensor factor in the Hilbert spaces of these two different systems, which satisfies the following constraint. if I have a tensor factor in a quantum mechanical Hilbert space and I have a quantum mechanical state, then that tensor factor has an impure state, a general density matrix. And these two systems will prescribe two different density matrices for that same common tensor factor in general. And it had better be that those two density matrices for every pair of causal diamonds are unitarily equivalent to each other. This is, for us, the quantum analog of the principle of general covariance. So we describe physics according to many different time-like trajectories. All of physics, as seen from the point of view of any given time-like trajectory, is described by its own Hilbert space and dynamics, but there are these consistency conditions between the dynamics along different trajectories. Those are very strong, very hard to satisfy. We have some examples that satisfy them. Okay. Now, as I said, causal diamonds are therefore defined by tensor factorization of the Hilbert space. Tensor factorization for infinite dimensional Hilbert spaces is actually a very touchy concept. But fortunately, there's another principle of quantum gravity directly related to what Bob Wald was telling you about, which tells you that in quantum gravity, we don't have to worry about infinite dimensional Hilbert spaces. And this is what's called the holographic principle. The holographic principle is a generalization of the Bekenstein-Hawking formula for black holes, generalization proposed first by Fischler and Susskind and then really worked out in detail by Busso. And that says the following thing. If I take any causal diamond, you can think of the boundary of that causal diamond. It's a null surface, has one null direction, and then transverse space-like sections. And those transverse space-like sections have areas. You look for the maximal area on the boundary of the diamond. That's called the holographic screen of the diamond. And that area, divided by 4, measured in Planck units, is supposed to be the entropy of the quantum system. Now, entropy in quantum mechanics refers to density matrices. And stated in the way I've stated it, I haven't yet told you which density matrix it is. But the reason you should believe this principle, we didn't discover this until we'd worked on this stuff for about 6 years. But there's a lovely paper by Ted Jacobson written more than 6 years before we started working that explains why I think you should believe in this as a fundamental principle of quantum gravity. What Ted showed is that if you apply the holographic principle to a generic causal diamond in a generic spacetime, and you take a point, the spacetime has low curvature compared to the Planck scale, so that I can have causal diamonds whose size in Planck units is very large, but are still very small compared to the curvature scale. In such a causal diamond, everything looks locally Minkowskian, and I can take over a calculation that Bill Unruh did a long time ago, the calculation of acceleration radiation. And what Ted showed is that if I think about energy as having to do with energy as measured along the trajectory of a maximally accelerated Rindler-Unruh trajectory, uniform acceleration, but just grazing the light cone. In that limit, if you apply the first law of thermodynamics, you obtain Einstein's equations, almost. I'll tell you what's missing. What's missing is the cosmological constant. The cosmological constant is not determined by Jacobson's argument, by local thermodynamics. What Jacobson's argument shows is that if you accept the area law, and you think of local thermodynamics, which is what we call hydrodynamics, you get Einstein's equations. The cosmological constant turns out to be related to an asymptotic boundary condition, not a local property of the space-time. the way you can think about the cosmological constant is if I take a causal diamond, it has both a proper time and an area of its holographic screen. And I want to think about taking the limit as proper time goes to infinity and area goes to infinity and see how those limits are related to each other. The sign of the cosmological constant has to do with the fact that if it's positive, proper time can go to infinity, but area stays fixed. If it's negative, it's the reverse. Area goes to infinity at fixed proper time. And if it's 0, they both go to infinity together following a particular power law rule. So the cosmological constant should not be thought of as a local property, and therefore the calculations we do of it in quantum field theory are just not supposed to be calculating the cosmological constant because they're calculating something that has to do with just a local region of space-time. So this is the first of many indications. Bob has already told you about some other ones in the last part of his talk, that quantum field theory is much more wrong when applied to gravitational systems than we thought it was. It's not just wrong in regions of high curvature and high energy density. It's wrong, it will turn out, in regions where the entropy is very large for what we'd like to think of as localized degrees of freedom. Okay. Now, something else that follows from Jacobson's point of view, if I give you a quantum system and it's got large distance scales in it, so I can do averaging of energies over and pressures and so on over large distance scales, then it obeys classical hydrodynamic equations, no matter how quantum mechanical it is. And what Ted's argument suggests to us is that generically we should think about Einstein's equations, and by extension, all classical field equations. I say that as someone who's done string theory, because in string theory, all fields come out effectively of fields that are associated with the gravitational field. So field equations should be thought of as hydrodynamics. In condensed matter physics, do you quantize hydrodynamics? And the answer is generically no. Generically, there are some underlying quantum degrees of freedom. They give rise to classical hydrodynamic equations. If you quantize those equations in a generic state of the quantum system, you do not get a correct description of excitations. If you have a system that has a unique ground state, and you look at small fluctuations around that ground state, then you do quantize hydrodynamics, and you get things called phonons and various other kinds of quasi-particle excitations. The demonstration in string theory that certain theories of quantum gravity reduce at low energy to quantum field theory is, I claim, nothing but this principle applied to systems in asymptotically flat space-time and asymptotically anti-de Sitter space-time, where the gravitational system has a unique ground state, and the quantum field theory is describing small fluctuations around that ground state. It does not justify using quantum field theory in every low energy density situation. In particular, not to analyze the properties of states of black holes for reasons very analogous to the ones that Bob told us about. And also, I would claim, to analyze the quantum mechanics of what's going on during what we call inflation. So let me turn now to talking about holographic space-time models of cosmology. There are a couple of these models we've constructed. These models are not all supposed to correspond to the real world, and the ones that we understand best do not correspond to the real world. But they're rather interesting. They correspond to situations in which the degrees of freedom of the system, about which I'll tell you a little bit in just a minute, are at all times maximally excited, so the system is exploring its entire Hilbert space. In holographic space-time, the statement that there's a Big Bang or beginning of time just suggests that our quantum mechanical system has a beginning to it. There's no contradiction with any rule of quantum mechanics of assuming a beginning as long as I don't assume that the Hamiltonian is time independent. However, as I told you, if I think about starting from a beginning in holographic space-time and take a little time into the future, then I have a very small causal diamond. So the Hamiltonian should split up into two parts, one of which acts on only a very small number of degrees of freedom. At the next instant, the causal diamond is larger, so there should be a shift of degrees of freedom from those that were outside to those that were inside. The Hamiltonian must be time dependent. And the beginning of time is just naturally the place where the causal diamond is smallest. There's nothing singular about it. If we then say that the dynamics as we go forward in time is completely random, in a technical sense that I won't bother to, or won't have time to talk about, we can argue that at the initial stage of the universe, everything completely saturates the covariant entropy bound. That's a really easy argument. If we further assume that as the causal diamond gets larger and larger, we approach a Hamiltonian which has the scaling properties of a 1 plus 1 dimensional conformal field theory with certain characteristic values of the C parameter of that theory, etc. If we do that, we derive from the quantum mechanics an effective coarse-grained description of how the entropy, energy density, and size of the horizon volume are growing in this system according to the rules relating quantum mechanics to geometry that I told you about, that corresponds to a flat FRW universe with equation of state P equals rho. If I just legislate that I'm going to stop the growth of the Hilbert space, that is to say that the original Hilbert space in which this all takes place actually had a maximum dimension, and this causal diamond grows until I get to the maximum, and then the Hamiltonian becomes time independent. We, instead of a P equals rho FRW, we describe an FRW that has a mixture of two components, P equals rho and P equals minus rho, and evolves in the future to an asymptotically de Sitter space with a value of the cosmological constant that's put in as an asymptotic boundary condition. Nothing determines it. So this de Sitter space that I describe is only a single horizon volume of de Sitter space. And if you set up the whole set of trajectories, what you find in this system is that if I put in the de Sitter boundary condition, trajectories that are far enough apart from each other in a very specified sense just don't talk to each other at all, as one would expect in the conventional classical space-time picture of de Sitter space. But the quantum mechanics along any given trajectory actually just has a finite number of states. And it just becomes an equilibrium system because the Hamiltonian is random. Now, that's a universe. It satisfies all the rules we can think of. It is a derivation of a particular classical solution of general relativity from a quantum mechanical system. Note, in this whole setup, the space-time geometry is not, I repeat not, a fluctuating quantum variable. Everything about the space-time geometry, the causal properties and the conformal factor, which is determined by areas, which are determined by dimensions of tensor factor Hilbert spaces, all of those things are non-fluctuating variables that are specified by how the Hamiltonian acts, but they're not the actual quantum mechanical operators. The quantum operators themselves live on the holographic screen, and for reasons I don't have time to explain to you, have to be chosen to be sections of the spinor bundle on the holographic screen. They're spinor variables, but in the transverse dimensions, except that you put a cutoff on the modes of the Dirac equation. The transverse screen is a compact Euclidean space. It's got two dimensions, which, since we're trying to model the world that we know, those two dimensions have the geometry of a two-sphere. That two-sphere has a finite radius, which is determined by the cutoff on the Dirac equation. And in addition, there are some compact dimensions, and the algebra of the variables specifies everything that this theory knows about the geometry of the compact dimensions. This is the place where you're going to have to believe me. If one believes this formalism, different choices of compact internal spaces do not correspond to states in the same theory, but rather to different theories. This is something I've argued within the context of string theory independently of this formalism. I think it's just true. So these variables live on the holographic screen. What do they have to do with particles? It turns out that localized excitations in the bulk of space-time correspond to constrained states of the variables on the screen. States in which there are little jets of energy coming out at fixed finite points on the screen, and every place else the energy coming out is zero. This is a very loose description. It would take me hours to explain the details to you. But the important thing you should take away from this is that particles, black holes in the bulk, all of them are constrained degrees of freedom in a large causal diamond with a radius much larger than the radius of the black hole. In order to get a universe in which there are localized excitations, this is what we call the era of inflation, what we do is we take the situation I led up to before with some value of the cosmological constant, and we arrange that copies of that system that are independent of each other now slowly begin to interact. That period of slow interaction is the period where the apparent horizon expands to incorporate many horizon volumes of de Sitter space. I'm just trying to make a parallel with the conventional inflationary picture. Inflation is not de Sitter space. Inflation differs from de Sitter space, and all its observational consequences differ from those of de Sitter space because precisely of the fact that we, at our very late times, see many, many of the local de Sitter horizon volumes. Modeling that in this quantum mechanical system turns out to be a constraint. The constraint says, when translated into inflationary terms, the more E-folds you require, the more horizon volumes you ask to see, the less entropy the initial state has. Okay? However, there's a countervailing phenomenon. When I finish with inflation, I can ask, what kind of universe am I left with? Well, each of these independent horizon volumes of de Sitter space is a little maximal entropy localized system, and it behaves like a black hole with a radius which is equal to the radius of the original de Sitter space. Remember, I'm now talking about a time where the radius of the apparent horizon is much larger than that, by a factor of e to the ne, and now a competition starts to occur. A universe with localized excitations that are just black holes can do two different things. Either the black holes can radiate and dump all of their energy into particles before they start to collide and coalesce and collapse with each other, making bigger black holes that radiate more slowly, and giving a universe that's totally uninteresting because all that's ever in it is a bunch of black holes. Or they can radiate away completely before they start to collide. That process, it turns out, gives us a lower bound on the number of E-folds. So counting of entropy of initial conditions suggests we want to have a minimum number of E-folds. This condition that the universe actually at some point become dominated by radiation rather than just a gas of big uninteresting black holes, that condition puts a lower bound on the number of E-folds. Our very crude estimate of that gives about 10 to the 5 factors, a factor of 10 to the 5 in scale, which is enough to accommodate what we see in the sky in the microwave background and large-scale structure, but not galaxy formation. So we don't know how to think about that. Maybe we need to impose galaxy formation as one of the criteria. I don't actually know how to deal with that discrepancy. At any rate, if I take the inflationary horizon radius to be of order the Hubble radius at the gut scale, this process, the one that makes a successful radiation-dominated universe, reheats the universe to a temperature of order 10 to the 13th GeV. That's hot enough that all of the worries one might have had about having a lot of little primordial black holes in the universe are not relevant, okay, because we never get to see that era. And, okay, so now that was the takeaway. I wanted to start to outline a little bit more of the details of this. I've told you some of this stuff already. In fact, I've told you almost all of this stuff. Okay, let me tell you about the predictions from this model of inflation. The predictions of this model of inflation give rise to fluctuations. Why do they give rise to fluctuations? Because the universe at a certain time consists of a collection of black holes of a certain average size, but that size is actually dynamically changing all the time, and there are fluctuations that are given, roughly speaking, by 1 over the square root of the entropy, as in any statistical system. That gives you an estimate of the size of the fluctuations. That's why I chose the radius to be about the gut scale. The local fluctuations are calculated in the quantum theory. The thing that you need in order to fit the data, and this is both something that I'm sort of proud of because we sort of pointed this out, but I'm sad about because it means it's very hard to test theories of inflation. All you really need to fit the data is the standard laws of cosmological perturbation theory for the classical Einstein equations, plus the fact that the curvature fluctuations themselves are calculated in terms of quantum fluctuations of commuting operators in some quantum theory, which obey approximately the symmetry of SO1, 4, the symmetry of classical de Sitter space. That's enough to fit all the data we currently have. The details of the fit have to do with what you assume the background FRW metric is as it evolves from the inflationary era to the matter-dominated era. By tuning that function, you can fit anything we've yet seen in the sky. This model does make definitive predictions that are different from standard inflation. Those predictions all have to do with the tensor fluctuations. And we got very excited when the BICEP people said, maybe we'd measure them because Dick Bond had told me we were never going to see them with enough accuracy to distinguish our predictions from those of typical slow roll inflation. The most dramatic part of the story has to do with the 3-point function of tensor fluctuation. That probably will not be measured in the lifetime of anybody sitting in this room. I'm sad about that, but that's the way it goes. The data on inflation is not fine enough to distinguish between theories to a large extent. We can predict things consistent with data, but that's really a sad thing rather than a happy thing. Important thing to emphasize, quantum effective field theory is nowhere valid any time during this regime. The degrees of freedom don't look like quantum fields. They're the only time you can start to apply ideas from quantum field theory is after the black holes have decayed, the universe is radiation dominated, and the localized entropy is all contained in particles. Before that, quantum field theory is just not a good approximation. Now, I want to try to explain to you this idea about the connection between low entropy and locality. So I told you about the variables being spinors on the holographic screen. You can derive from those spinors, from bilinears in those spinors, certain matrices. Now, those matrices are not quantum mechanical operators. Each matrix element of those matrices is a quantum mechanical operator. If we happen to be in a quantum state in which, to a good approximation and for a long time, the matrices look diagonal in this way, with a bunch of blocks, that if the Hamiltonian is also a sum, a trace of a polynomial in those matrices, okay, which to first approximation doesn't change a state that has the matrices equal to 0 there, and then it starts to change it slowly. If the Hamiltonian preserves this form for a long time, then you can treat these independent blocks as separate entities. They don't interact with each other to first approximation. The creation and annihilation of off-diagonal matrix elements gives rise to interactions between the different blocks. If you choose the coefficients in your polynomial appropriately, you can show that when the blocks are in a causal diamond that's very large, those interactions lead to the Newtonian force between blocks. These are the things that play the role of particles, these separate blocks. They're either particles or black holes. If the block degrees of freedom are in a random ergodic state, then they act like black holes. They're a thermal system, they have an entropy, and so on. If they're in certain very particular states, you can show that the block degrees of freedom look like massless relativistic particles. So the same system has excitations in it that have the properties of black holes being thermalized. Very importantly, both the localized black holes and the localized particles only make sense as excitations in states where the off-diagonal matrix elements, which I remind you again are quantum mechanical operators, in states where those are 0, those are states of very low entropy, because if the blocks are much smaller than the big block, then those states have most of the degrees of freedom set equal to 0. They're in a particular state. Okay? So that's the connection in this formalism between locality and low entropy. The low entropy initial state of the universe is, for us, a necessity in order to get any kind of localized excitations at all. And it's because of this property of the dynamics that locality comes out. Notice, by the way, there's a usual, if I look at this Hamiltonian, there's an invariance of permutation of the blocks. That turns into, in this theory, the permutation statistics of particle states. And so That's something those of you who know my old work from the 1990s on matrix theory should be familiar with that concept. Those of you who don't won't be. Okay. So what I've claimed to you, and not demonstrated to you in this talk, is that with an appropriate choice of Hamiltonian and using Jacobson's ideas about how to map a quantum theory of this type into a space-time metric, we get a Hamiltonian that goes from p equals rho to inflation to a dilute black hole gas, after which we can use standard properties of Hawking radiation to see what else is going to happen. So the cosmology then becomes vanilla, and you can think about it in the usual particle physics terms after the black hole's decay. I want to emphasize that flatness, homogeneity, and isotropy follow in this system for arbitrary initial states independently of whether inflation occurred or not. Inflation has nothing to do with those properties of the universe in this model. That means that our a priori lower bound on the number of e-folds of inflation is not the same as the one that comes from standard inflationary models where you have to have inflated enough that our entire universe got flattened out. It's much weaker than that. It comes only from this condition I told you about, that the black holes decay before they collide and coalesce. And that leads to a much smaller number of e-folds, barely enough to explain the data that we see, way less than 60. Why is this relevant, or might it be relevant? In standard cosmological perturbation theory, the ratio between the tensor and scalar modes of fluctuation has a factor of epsilon in it, where epsilon is the slow roll parameter. The more e-folds of inflation you want, the smaller epsilon has to be, and so the bigger you predict the scalar modes are than the tensor modes. So the fact that typical inflation models predict very small r comes partly from the fact that we're insisting on having 60 e-folds of inflation. This model does not need that, and so nominally I might have guessed that this model would lead to tensor modes that are observable. Is that 1 or 0? That's 1. Okay, let me finish up, talk quickly about generalized cosmology. We have a model in which, this is a real model, in which the universe I've described so far is embedded as a trapped surface with a horizon area given by the cosmological constant embedded into a flat p equals rho FRW. Thinking about solutions of GR, there are obvious solutions where you have many such trapped surfaces, multiple marginally trapped surfaces in the p equals rho background with different values of the cosmological constant during inflation, the number of e-folds. And so this can lead to a framework where we have anthropic selection of these parameters. And apart from the connection that I certainly don't have time to tell you about between supersymmetry breaking and lambda, particle physics is not jumping around between these different states because, as I told you, most of the content of particle physics is programmed in the commutation relations, I assume, for the fundamental variables. So we get anthropic selection just of these parameters and not of all the others. As I said in George Ellis's talk, if you do anthropic selection of all the parameters in the standard model, you're in violent disagreement with experiment. Finally, these universes look like they're black holes embedded in the p equals rho background, and depending on initial conditions, which we can have no experimental information about whatsoever, they can collide with each other and interact. Those collisions can happen on any time scale. What we need to explain the data and avoid the problem that Don Page invented for us of Boltzmann brains is to have those collisions occur on a time scale longer than the time we've seen, but shorter than the time which you create many Boltzmann brains. Because that time is so incredibly long, it's easy to satisfy that criterion, and there's no way we'll ever be able to check it experimentally. It's, as I said, meta-cosmology, and I'll stop there before Bill pounds me.
Thank you very much. We have time for some questions. Yes.
So, Tom, there's a Big Bang hypersurface. So the model is going to be geodesically incomplete in the fast direction. But you said you're emphatic about the model not being singular.
Right.
So how does that work?
Okay.
Oh, sorry.
Okay, so that was Christopher Weaver from Rutgers. Chris, the way that works is that, as Jacobson explained to us, geometry is a thermodynamic, hydrodynamic approximation to the real quantum dynamics. It really sets in only when the size of the causal diamond is large enough. In our model, we don't get the p equals rho geometry from the first Planck instant. At the first Planck instant, our Hilbert space just has a very small number of dimensions. It's a kind of finite quantum mechanics. It gets bigger and bigger and bigger. The p equals rho behavior is a scaling behavior that sets in for relatively large times. And so the singularity is an extrapolation of that large time behavior back to t equals 0, where hydrodynamics fails because the system is too small.
Carlo, a short question, not a speech.
Okay, so I'll be short, I'll not be a question. I think that Jacobson 95 is an extremely beautiful paper. I don't think at all it implies that the geometry is hydrodynamical in that way. What goes into his derivation of the Einstein equation is much more than the area law. Is the existence of a metric, is the diffeomorphism invariant, is local covariance, and it's a long, long list of things, out of which not much can come out if not the Einstein equations. So I don't have time because Bill is looking at me with horrible eyes, but I just want to make this statement.
Thank you. Do you want to respond to his statement?
Well, I disagree with the last part because Ted explicitly showed how other things can come out if you change the area law into something else, and proposed that higher order terms, corrections to Einstein's equations, will come about precisely in that way, and it's the relation that Bob Wald showed between, generalized entropy for higher order equations, and that Ted did all of that. So,
one more short question, Jim. I'll allow you to ask this time. No, I'm allowing you to.
Thank you, Bill. Do you have a built-in arrow of time, or can you go both ways from the minimal dimensional Hilbert space?
Yeah, in the cosmology, there's a built-in arrow of time, which it comes about because of the fact that we assume that the interior of the causal diamond Hamiltonian acts on a small Hilbert space, and then a larger one, then a larger one, then a larger one. It doesn't, the Hamiltonian is time dependent, okay? So, you can try to take the inverses of all of those unitary operators. I'm not sure. The really important point to me is that built-in arrow of time does not imply the thermodynamic arrow of time. In our generic initial condition models, we end up with a universe that at all times has maximal entropy, consistent with the covariant entropy bound. There's no increase in entropy except by the fact that the causal diamond increases. You're in causal contact with more degrees of freedom. Those become completely thermalized on the time scale of the increase itself. And so the thermodynamic arrow of time is not a consequence of the built-in arrow of time, but rather of our imposition in certain models of these low entropy initial conditions of off-diagonal matrix elements vanishing in initial states.
Thank you. I've been ordered to cut off discussion at this point. Is there any announcement before the break? No.